Hello student, very good morning to all of you. Do you remember what were we discussing yesterday? I think we were discussing about the malonic ester and its synthetic application, and there what type of the group they are showing or exhibiting, what are the synthetic application of that malonic ester, we have discussed in detail. Today what we are going to discuss, let us look at here acetoacetic ester, and you are quite familiar with this word acetoacetic ester, or we can call it as ester acetoacetic, or we can call it as a beta keto ester, right? First of all, let us see the structure of it, right? Now the structure of it, and this one CH3 C double bond O, then CH2 C double bond O, OET. This is a structure of acetoacetic ester, or we can call it as a ethyl acetoacetate, or we can call it as a beta keto ester. Why it is a synthetically important? Because similar to as a malonic ester, it also has reactive methylene group. This CH2 group is called as a reactive methylene group. Why it is called as a reactive methylene group? While studying the detailed study of malonic ester, we have already learned what do you mean by the reactive methylene group. Reactive methylene group means what? The methylene group is flanked in between electron withdrawing group is known as reactive methylene group, and by using as a base it can easily get abstracted and form as a carbanion. And when that carbanion is formed, that carbanion means what? In an reaction, a negative part of the negative charge present on the chemical species or on the carbon carries as a negative charge, that type of the species is known as a carbanion. And this carbanion is this reagent is a versatile reagent, or it is called as a synthetic application, because variety or the number of organic compound we can prepare by using this reagent, and therefore this acetoacetic ester or ethyl acetoacetate, or we can call it as a beta keto ester, is a very versatile organic compound. Variety of the compound or the number of organic compound we can prepare by using as this acetoacetic ester. And we already studied these acetoacetic ester, who is prepared this first time in the laboratory. Let me tell you, we already learned that is a Claisen ester condensation reaction, right? In a Claisen condensation reaction, there we have seen Claisen is a scientist name. He prepared that compound in the laboratory first time, and therefore it is known as Claisen ester condensation reaction. And what are the starting material he has taken? There one is a two molecules, same molecule of the ethyl acetate treated with the sodium ethoxide, and the resulting product obtained or got is known as a ethyl acetoacetate. And why it is a synthetically useful or beneficial? Because it containing as a reactive methylene group, and that reactive, the speciality or the property of that reactive methylene group easily form the carbanion. Once that carbanion is formed, or that carbanion is called as a nucleophile. Means nucleophile, as we know that nucleophile can attack on the alkyl halide, and there will be a formation of the new carbon-carbon bond. And due to this reason, that synthetically, or what we can call it as far as organic chemistry is concerned, it is a very, very useful. Let me revise this again, how that Claisen ester condensation, and he has taken as a 2 moles of ethyl acetate, ethyl acetate C double bond O, then OET, that will be treated with sodium ethoxide, and the resulting compound form is a CH3 C double bond O, CH2 C double bond O, and OET. This is called as a ethyl acetoacetate, and this reaction is known as a Claisen ester condensation. 2 molecules condense together, resulting the product is a acetoacetic ester, or it is called as a beta keto ester, because it has a reactive methylene group where we can that reactive whenever the carbanion form, and that carbanion are well stabilized due to the minus I inductive effect and the minus R inductive effect. Suppose this is the acetoacetic ester here, CH3 C double bond O, then CH2 C double bond O, OAT. If you use here as again as a base is a sodium ethoxide, what it will do, it will abstract the proton from here like this. I am writing for clarity purpose. This way, this ethoxide can abstract the proton and form as a negative charge over here, and you are going to get here CH3, then C double bond O, then CH. I am writing that negative charge like this, CH, C double bond O, ET. Now, what is going to happen? These negative charge coming here and forming, these get stabilized due to the resonance. This is a double-headed arrow, or what we can call it as a resonating arrow, and therefore CH3, then O minus double bond CH, then C double bond O, OET. Again, we can draw the resonating structure of this negative charge forming as a bond between this carbon atom and this oxygen atom. This double bond concentrate the electron density over here, and you are going to get over here CH3 C double bond O, CH minus, and then here C double bond O, then OET. Again we can draw the resonating structure. This negative charge comes over there, and then negative charge on that oxygen atom. You will be getting here CH3 C double bond O, CH double bond CO minus, and then OT, etc. So in this way, that carbanions are well stabilized due to the resonance, and that's why it has a synthetic application. Synthetic application of this synthetic application of that ethyl acetate, this ethyl acetoacetate or beta keto ester are well stabilized due to the resonance. Let us see first one, a synthesis of substituted acetone, that is a alkylation, and as this is a keto ester, this carbanion is a better stabilized than that of malonic ester. If you compare the carbanion stability, as we know that there are the 4 factors which can stabilize the carbanion, and that carbanion can be well stabilized due to the resonating structure better than the malonic ester. Now let us see here the synthesis of substituted acetone. Synthesis or preparation of synthesis of substituted acetone. Synthesis of substituted acetone, that is called as a alkylation. Maybe as a, here we can call it as a monoalkylation. First let us see here, first one is a monoalkylation, and then after that we will see the dialkylation. Let us see here monoalkylation, CH3 C double bond O, CH2 C double bond O, then OET. First of all, what is the reagent we are going to use here? The reagent will be sodium ethoxide. Second one will be the RX, that is alkyl halide. Third one maybe as a hydrolysis H2O in presence of H plus, and fourth one is a heating, there is a decarboxylation, CO2 is get evolve in this process, that type of the process is called as a decarboxylation. And fifth one may be as a H2O in presence of H plus, it is termed as a hydrolysis. If you do all these things together, the resulting compound will be obtained here, CH3, then C double bond O, then CH, and here I am writing one of the hydrogen atom over here, and here is a R part. If you observe this final structure carefully, what do you see over here? Look at here, this part, one part over here, another part will be there, and this part will be there. So let us see here, if you observe carefully, the CS3 C double, this treatment we have seen during the malonic ester, same reagent we are using. Here NaO2, that step is called as abstraction of proton, Rx means alkylation, and H2O in presence of H plus is called as a hydrolysis, and heat minus CO2 is called as a decarboxylation, means carbon dioxide is evolved during this process, and H2O in presence of H plus, this is called as a protonation. Now most of the students get confused between this, but let me tell you, this is called as a hydrolysis. This process is known as a, even though it is the same, but the role playing here are the totally different. Here in the final stage there is a abstraction, means abstraction of proton, means resulting the hydrogen atom is attached to this carbon atom, and finally we are getting as a this type of the compound. This is called as a monoalkylation. Okay, and now when you observe this structure carefully, what do you see over here? CH3 C double bond O CH, this part which is coming from the acetoacetic ester, this is a acetoacetic ester, and here R, this part is coming from the alkyl halide, and this H, from where it is coming? It is coming from the solvent, that is a protonation. So this is the, what we can call it as a analysis of this target molecule, and as we know that target molecule means what? Whose molecule, the molecule whose synthesis being planned is called as a target molecule. Now let us look at a second step, that is called as a dialkylation. Dialkylation. Another one more point I am going to mention over here, this one is called as a monosubstituted acetone, or we can call it as a alpha monosubstituted acetone, alpha monosubstituted acetone, and now is a dialkylation is nothing but as a alpha disubstituted acetone. And let us see here, the starting compound is the same, CH3 C double bond O, then CH2 C double bond O OET. This is a again acetoacetic ester, once again, then use as a same reagent. Number one is a first one sodium ethoxide NaOET, second one will be the alkyl halide Rx. Then in the third step, what you are going to do next? Third step, you again use as a sodium ethoxide NaOET, and then in the fourth step I am writing here because there is a no space available here, and that's why I am showing here. Fourth one will be the Rx. R may be as a different one, you can take aromatic or you can take as a aryl group over there, but specifically you can take as a alkyl halide over there. Then fifth one, there is a hydrolysis H2O in presence of the H plus, and sixth one you can use as a heat decarboxylation minus CO2, and seventh one will be the H2O in presence of H plus, that is a protonation. After doing all these things together, the resulting compound obtained will be this one, CH3, C double bond O, again CH, then I am writing here R and here also as a R. Now if you observe this compound carefully, what do you observe over here? Look at here, CH3, C double bond O, and this carbon atom, this part is coming from this versatile synthon. Versatile synthon are the synthetic reagent which is acetoacetic ester or ester acetoacetate or beta keto ester. This part is coming from that, and now this one of the R, or you can call it as a second, maybe you to distinguish between these two R, one you can call it as just as a R and second will be as a double dash or single dash, means there is a double alkylation, and that's why I am mentioning here is a dialkylation. So in this way we can prepare this dialkylation, or this is a alpha disubstituted acetone. This is alpha disubstituted acetone. This is a alpha disubstituted acetone. So this is what we can call it as. In this way we can prepare monoalkylation as well as dialkylation in the laboratory using as this method. Now let us start the synthetic application of this, because this is the second synthetic reagent which we are using here for the preparation of monosubstituted or disubstituted acetone. Let us take the one example over here. Now consider the synthesis of consider the synthesis of consider the synthesis of 3-ethyl 2-pentanone. Synthesis of 3-ethyl 2-pentanone. 3-ethyl 2-pentanone. So that you have to prepare, that you have to synthesize in the by using as a so our question, how the question appear, the question may be like this: how will you prepare or how will you synthesize 3-ethyl 2-pentanone using acetoacetic ester? So now let us see here. First of all, see the structure of this 3-ethyl 2-pentanone. Pent clearly indicate that there are the 5 carbon atoms are there. So you can first write down 1, 2, 3, 4 and 5 carbon atom. Let us see here to what do you mean by the to? What it indicate? To indicate the presence of last suffix C over here, ONE, that indicate as a carbonyl group present at 2 position. So that is the 2 indicate as a 2 position. If you number from this side 1, 2, 3, 4 and 5, look at 2 position is a carbonyl group, and at 3 position there is a ethyl group. The ethyl group you can write CH2CH3, or you can just write as a C2H5. You can write either this way or this way, it doesn't matter, one and the same thing it is. You can write CH2CH3 or C2H5, one and the same thing. Okay, now let us see here remaining. As we know that carbon has 4 bonds. Here this is a terminal carbon, there you should attach as a, you can place 3 hydrogen atom here. Here I am placing as a 3 hydrogen atom. Look at here, 1 and 2 bond is already just placing as a 1 CH 2 hydrogen atom. Look at here, 1 2 3 bond is there, so that I am placing only 1 hydrogen atom. The reason behind it, it has already has a 3 bond, and therefore I am placing only as a 1 hydrogen atom. Look at this carbon atom, there are the 4 bond, 1 2 3 and 4. Therefore this is the correct structure of 3-ethyl 2-pentanone. Now do the planning. Planning means you have to analyze it, how you can prepare this compound in the laboratory. That way you have to think, you have to increase your thinking power over here. Then and then if some of the students may write as this structure, or for suitability I am writing this compound like this, C double bond O, then C CH, then CH2 CH3, another one CH2 and the CH3. You can write or you can represent this structure either this way or this way, one and the same thing. Now the planning over here, and as we know that planning is a very important as far as synthesizing as an organic compound. So look at here, CH3, and then this part I am marking this part. From where this part is coming? This part is coming from acetoacetic ester or beta keto ester. Now I am marking here also, and this marked position or marked part is again coming from the alkyl halide, specifically ethyl halide or ethyl bromide. You can use ethyl chloride. Look at here also, here also CH3 CH2, this part also coming from the same alkyl part. So double alkylation you have to do over here, and you will get your resulting compound. Means here the synthesis of ethyl 3-ethyl 2-pentanone using as a acetoacetic ester. Let's start the synthesis. Your starting material, your substrate, or what we can call it as your precursor, should be the acetoacetic ester. Let us see here, CH3 C double bond O, then CH CH2 CH3, and here CH2 and the CH3. Planning we have already discussed. Now first one, what you have to do, treat with this sodium ethoxide. Sodium ethoxide, it is a base. The function of base to abstract the highly acidic proton, which will which proton is going to abstract. Sorry, here is a, this is not the structure, this is our final structure. Here the structure will be CH2 C double bond O and OET. This is a structure of acetoacetic ester, or you can call it as a ethyl acetate or beta keto ester. Now sodium ethoxide, what it will do? It will abstract the acidic proton, which is a methylene proton. Why that methylene proton? There are different protons are present. This CH3, again CH2 CH3. There are different protons are present. But why sodium ethoxide abstracting proton from the methylene? Because it is a reactive methylene group, and when it form as a carbanion, and that carbanion are well stabilized due to the resonance, and that is the reason why it is abstracting the proton from this side. H minus charge, C double bond O and OET. That's it. This is a carbanion. Here you can write Na plus over here, or there is no need to write. You write it or don't write, it doesn't matter. It doesn't make any difference. But for the clarities to understand, you can mention there as a Na plus. Okay. Now in the next step, what is going to happen? Then CH3, then CH2Br. This is a ethyl bromide. This is a bromination, ethyl bromide alkylation we are carrying out. Here this negative charge attacking on that CH2, and the Br is a departure group. In this way get departed, and you are going to get over here this one CH3, C double bond O, then CH. This CH3 I am writing in this way, CH2 and CH3, other part C double bond O and OT, it remains as it is. What should I do now? And now next one is a hydrolysis or base treatment. Here you carry out the base treatment, or if you do the hydrolysis, what hydrolysis can do? Hydrolysis means ester group is converted into as acid, and that acidic proton is highly acidic in nature, and that makes the problem because while treatment with the base, and therefore before that you have to use as a give the treatment of that base sodium ethoxide. What it will do, here is one of the proton there, it can abstract that proton, and you will get the formation of, again is one more carbanion, C double bond O, C minus charge over there, this CH2, CH3, another one C double bond O and OET. In this way, this carbanion again is a well stabilized because it is present in between as a two flanked carbonyl group, and that's why it is a stable one. And next one, do the next CH3, then CH2Br. Then again is alkylation. What is going to happen now? This negative charge is going to attack on that CH2. Again there are the two choices are there. One is a CH3 and CH2. Why that arrow I am resting on that CH2? Why not on the CH3? Because the CH2 attached to bromine atom. Bromine is a highly electronegative in nature, pulling the electron density toward itself, making that carbon atom is more electrophilic in nature, and therefore preferentially this carbanion is attacking on that carbon atom, and the resulting compound found will be this one CH3, C double bond O, then here CH2, CH3, C double bond O, OET, and then CH2 and CH3, right? So here is a, you remember here CH2 and the CH3 over there. And now after that hydrolysis, and as we know that H2O in presence of H plus. Hydrolysis, it is a process to convert ester group into as a acid group or carboxylic group, and therefore you are going to get over here CH3, then C double bond O, then here carbon, then CH2 and this CH3 group, and here also as a CH2 and the CH3, here C double bond O and H. This type of the compound we are getting here. For clarity I am showing that compound over here. So this one I am again writing here CH3, then C double bond O, then here upper side CH2 CH3, then downside CH2 CH3, and here acid group C double bond O and OH, and after that there is a heating, means CO2 is evolved. This process is called as a decarboxylation. Decarboxylation is done over here, and what you are going to get here, this sigma bond moving like this and double bond revolving around it, and the negative charge coming on this carbon atom, and the resulting compound you are going to get over here CH3, C double bond O, then here CH2, CH3, another one CH2 and the CH3, minor charge over there, the carbanion again is formed in this case. Now this carbanion will pick up the proton from the solvent, and generally here we are using H2O in presence of H plus, and this process is known as protonation. This process is known as a protonation. In the protonation, what will happen? This carbanion will pick up the proton from here, and the resulting compound we are getting CH3, C double bond O, then I am writing here CH, then CH2, CH3, and another ethyl group I am writing here CH2 and the CH3. This is the structure of this is nothing but as a 3-ethyl 2-pentanone. In this way we can prepare the 3-ethyl 2-pentanone. So as per as the exam point of view, 3 mark question always appear on the question, maybe as a like this: how will you synthesize 3-ethyl 2-pentanone using acetoacetic ester? Half of the answer is already included in the question, because they have given from where you have to prepare and which you have to prepare, because starting compound also given as well as final compound also given. You just have to mention the appropriate or the proper reagent, and finally you will get your desired products. So that is the thing you have to do in the exam. So now let us see the second. What are the noticeable point here? I already discussed during that planning. You noticed this part CH3 C double bond O C, which is coming from the acetoacetic ester, and this part CH2 CH3, this marked part which is coming from the alkyl halide. I am again marking another part which is also coming as the, means this is the double alkylation, or we can call it as a alpha dialkylation. We are synthesizing the alpha substituted monoacetone or mono substituted acetone, or we can call it as a alpha disubstituted acetone. So in this way we have clearly synthesize any target molecule starting from that acetoacetic ester. Let us see the second example over here. Consider the synthesis of 3-methyl-2-hexanone. Now here we are consider the synthesis of now here second point we are going to discuss over here. We are talking about the synthesis of substituted acetone, alkylation. Second point we are going to consider over here. Consider the synthesis of 3-methyl-2-hexanone. Consider the synthesis of 3-methyl-2-hexanone. Look at here, 2-hexanone. So that is our target molecule. Target molecule, we know that this is a new term to you, but next lecture, next chapter is a retrosynthetic analysis and application we are going to learn. At that time we will see this type of the term, this type of the terminology, important terminology we are going to learn during, because that is a new concept introducing at a T.Y.B.Sc level, because the rest of the thing we have learned something from your previous classes, but that retrosynthetic analysis is new to one, and the spectroscopy also as a new to one, that we are going to in the next time. But here let me see this, whatever compound is there, this type of the compound, whatever compound we are going to synthesize in the laboratory, that is called as a target molecule, means the molecule whose synthesis is being planned is called as a target molecule, and the starting material also given, or the question, how the question appear in the exam, how will you prepare the, or how will you synthesize 3-methyl 2-hexanone using acetoacetic ester. So first of all, let us draw the correct structure of this. So here the structure of 3-methyl hex, what it indicate? Hex indicate there are the 6 carbon atom in the straight chain. Let me draw that structure here. Let us see here 1, 2, 3, 4, 5 and 6. There are 6 carbon atom in the straight chain. Now look at these 3, 2, they are indicating the position of that particular functional group, that specific functional group. Look at here to indicate that the position of carbonyl group. So I am writing at 2 position, there will be a carbonyl group, right? Now look at here 3 position, means they are mentioning as a methyl, means at a 3 carbon atom it has methyl group CH3, right? Here is a CH3, and rest of the carbon atom you can place the appropriate hydrogen atom. Look at, this is a terminal carbon atom. I am placing 3 hydrogen atom. Why I am placing 3 hydrogen atom at this carbon atom? Because it has a 1 bond. So rest of the blank thing you can add the hydrogen atom, or you can place the hydrogen atom. Look at this carbon atom, there are 4 bonds, 1, 2, 3, 4. Here 1, 2, 3. So how many hydrogen atom I should place here? Here I am placing as a 1 hydrogen atom. Look at here I am placing 2 hydrogen atom, here 2, and here this is again terminal CH3. This is our the structure of the target molecule is this one. And now this target molecule now is a planning. Now you have to plan it, and everything is depend upon the planning. Because if you have a proper planning, then you can achieve whatever difficult goals are there, whatever difficult things are there, you can achieve it if you do the proper planning. Proper planning is needed for the in every case, or in every area, you in every aspect you have to keep the approach, or your perspective should be the proper one. So let us look at here. So I am marking here, I am planning. So here remember I am marking. So you just tell me from here these are the things are coming. So I am marked some of the one of the hydrogen atom I am writing as a like this. Okay, there are the what we can call, I am marking as there are the 4 parts there. You have to just tell me just by observing this structure which part is coming from which. Suppose let us see over here CH3, C double bond O and H. It is specifically coming from acetoacetic ester. This is one of the important point you notice here, right? Now look at one methyl group. This methyl group which is obtained, which is coming from methyl bromide. Remember here, as far as the T.Y.B.Sc is concerned, you remember it is coming from the methyl bromide. Just you have to attach over is a bromine atom. Now look at this one, 1, 2, 3 carbon atoms are there, and this part also coming from the alkyl halide. Which alkyl halide here? Here is a propyl bromide, or you can call it as a 1-bromopropane. right? This part from where it is coming, it may coming from the you can call it as a 1-bromopropane, or you can call it as a 1-chloropropane, 1-iodo-propane, or 1-fluoropropane, but specifically you mention as a bromo over here. That is the best way to remember. This is a planning, right? Understood? Here are the 4 points. And this hydrogen atom, from where this hydrogen atom is coming here, this hydrogen atom is coming from the solvent in the protonation process. This is a simple planning of this compound. Now let us start the synthesis of this. Now how do you synthesize? First, half mark is given to as a planning, and half mark is given to the synthesis of this compound. Now starting compound also mentioning how will you synthesize 3-methyl-2-hexanone using acetoacetic ester or beta-keto ester or ethyl acetoacetate. It is a what we can call it as a starting material. Let us see over here, CH3 C double bond O, then CH2 C double bond O, OET. This is a starting material, right? First one, do the treatment with sodium ethoxide. Sodium ethoxide is a base which will abstract the proton from here, CH3 C double bond O, form as a carbanion, and these carbanion are well stabilized due to the resonance, as we know that, and this we can treat with this methyl bromide, CH3 bar. You can take methyl bromide first time, or you can take ethyl bromide, whatever you like it, you can take it. So now this negative charge is going to attack on that CH3, Br is a departure, so that you are going to get over here CH3 C double bond O, then CH methyl group I am writing over here, then C double bond O, then OET, right? Then next one, what I should do now, again I am treating with that sodium ethoxide, NaOET, another hydrogen atom present on that carbon atom, it get abstracted and we get here C double bond O, C here CH3 minor charge, we will get carbanion ion over here C double bond O, OET, right? Now what should I do? Next one I am going to treat this compound with CH3, then CH2 Br, right? Now this negative charge is going to attack on this carbon atom, this methyl group, not on this. Some of the students are attacking that. So remember, this one is more electrophilic in nature, and therefore carbanion is going to attack on that particular CH2, and you are going to get CH3 C double bond O, then here CH3, then here CH2 CH3, and here C double bond O, OET. This is a compound we got over here. Now next one, what I am going to do here, next will be the hydrolysis, H2O in presence of H plus. What the hydrolysis can do over here, hydrolysis will convert that ester group into as acid, and you are going to get here CH3 C double bond O, then CH3, and finally CH2 CH3, here C double bond O, OET, right? And after that, what I am, not this one, there is a hydrolysis, means ester group is going to convert it to as a acid. Now next will be the heat. There is a elimination of carbon dioxide. That process is known as a decarboxylation. Decarboxylation can be carried out in this way. This form over there, this double bond revolving around it, and there will be a formation of carbanion, and you are going to get CH3 C double bond O. I am writing here this CH3, and finally CH2 and CH3 minor charge over there, and then this H2O in presence of H plus, This process is known as a protonation, right? And after the protonation, what is going to happen? It will pick up the proton from here, and you are going to get CH3, then C double bond O, then CH, 1 CH3 I am writing here, and this ethyl group I am writing, propyl group I am writing this manner, and this is nothing but our target molecule. So I think in this way we can prepare. So some of the application we will see next time. I think let us stop today here. Have a nice day. Thank you.